X-ray fluorescence is an analytical technique in which X-rays tear electrons from the innermost shells of atoms. When the electrons in the upper layers return to the levels that have been left empty, X-rays are emitted with energies that are characteristic of each chemical element. If the energy of the emitted X-rays is measured, that is, the X-ray fluorescence spectrum is obtained, it is possible to know which chemical elements are in the sample. In this video I will show how an X-ray spectrometer has been built. In a following video I will show how X-ray fluorescence works. What you're looking at now is how a homemade X-ray spectrometer detects X-rays emitted by an americium-241 source and classifies them according to their energy. The construction and tuning of a X-ray fluorescence apparatus begins with the spectrometer. In this one I have used as a detector the humble BPW34 photodiode, which costs around €1. X-ray photons cause ionization within the semiconductor of the photodiode. Each photon gives rise to a small amount of charge of a magnitude proportional to the energy of the photon. The circuit that transforms this charge into a voltage is called CSA, for charge-sensitive amplifier. In the case of X-rays, the voltage of the pulses given by the CSA is very small, only a few millivolts, which is why it is so important to reduce noise as much as possible. The CSA signals are amplified and given a shape appropriated for capture, with a circuit configured as a differentiator followed by two integrators. After many tests it has been proven that a very effective CSA for X-ray spectroscopy is the one described by Bertuccio and co-workers in 1992. A novel charge-sensitive preamplifier without the feedback resistor. Ramirez, in 2008, made small modifications to the circuit. Later, in 2020, Todd and his co-workers used a simplified version of the circuit coupled to the ion detector in a mass spectrometer. This circuit also detects X-rays well but, unlike the previous ones, it has an exaggerated lack of linearity. It should be noted that one thing is detecting X-rays and another measuring their energy to obtain a spectrum with a reasonable resolution. In order to obtain X-ray spectra with a PIN photodiode, it is essential that the circuit gives little electronic noise. The resolution of the signals in the spectrum is determined directly by noise. The width of a signal at mid-height is about twice the standard deviation of noise. The width of the signal at the base is about 5 times this standard deviation. At room temperature, an acceptable resolution can only be achieved with small photodiodes. If working with larger photodiodes, or with more than one photodiode in parallel, it is necessary to cool down to reduce noise. The detector circuit is by far the most delicate part of the assembly. Electrical noise can originate from the photodiode, transistors or resistors, due to thermal effects, but it can be greatly reduced if the detector cools down. If a Peltier cell is used, it can be easily cooled to -15 C, but you must avoid introducing noise due to the power supply, the fan or the cooling water circulation pump. Noise can also be due to electromagnetic waves from the outside, and to reduce it the circuits must be placed well shielded inside a metallic box. To minimize noise, the circuits are powered by batteries. The shaped signals are captured with a National Instruments NIMYDAQ module running with LabVIEW. Since the maximum capture rate of this module is 200 kilosamples by second, the signals are roughly Gaussian-shaped with a rise time of about 30 microseconds. In the program, an additional treatment is carried out with LabVIEW signal filters, low-pass, high-pass and band-stop, to reduce noise a bit more. Blocks of measurements are taken, and within each block the signals within predetermined thresholds are detected. The voltage of each signal is measured. Signals that may be superimposed are discarded, and the histogram is made plotting the number of signals at each voltage. The spectrum can be calibrated in energy using a X-ray source, as americium-241, which well-defined peaks. A future video will describe how this spectrometer can be used in X-ray fluorescence experiments. See you soon.